lecturer teaching in the intermediate school, and we're really happy to have Ruben Suare from Freeform today at the AA. So just a very sort of brief introduction, background. Ruben's actually trained as an architect and has worked in several companies such as CTEK that examines architecture and manufacturing. And in some sort of way, Ruben actually defies architecture, and we'll see why. And he has also an interesting background in terms of getting a business degree to help solidify the relationship between manufacturing and architecture. You'll see, hopefully today with our short time frame, but we'll see how he also collaborates closely with architects, designers, to come up with really innovative solutions for materials and also extremely sustainable solutions. And I think we're also looking forward to seeing the translucent wood panel system that you developed and invented. And let's welcome Ruben Suare. Okay.
Turn this on. Can you hear me okay? I don't like these microphones, so I'm just going to move them. I have this, so I can move around and raise my hands. I don't like to be stuck in front of a podium when I talk. Well, thank you. Thank you, Marisa, and thank you to the AA, the Architecture Association, for having me here to speak tonight. Hopefully you'll find this exciting. It's a little bit different, as perhaps you read the introduction on the pamphlet, where we're speaking about an idea of creating a business unit or a business model that is mainly set up of architects that work as an architectural office within a manufacturing facility, and that in itself is a little bit different. I don't know how many of you are familiar with Freeform, but I'm going to go briefly with, I'm going to start with an introduction to what Freeform is. We're literally a manufacturing facility. We make engineered resin panels. I'll talk about that for a minute. And then I will showcase 4 projects that 2 of them finished and 2 of them in the process of being finished, that will address in detail the ways in which we work, partnering with architects to, in some ways, really challenge the position that has been established in architecture for the last few decades, and break that a little bit and change the structure in which manufacturers really work with architects. I'll start with Freeform. Freeform is in itself a very innovative company. Since inception, let's see if I can get this pointer to work. There we go. So since inception, the company has been in a position in which the business model is mass customization. It's a little bit like what you see Dell being a business, where what you do is you order whatever you want. So you make your computer like this, like this, like this, like that. That is mass customization. We don't inventory any products because we have about 1 million combinations, 1 million options. And what you do is you work with Eco Resin panels, environmentally conscious, the fabrication process, I'll speak about that in a minute. And you embed different materials, wire meshes, fabrics within those panels. We press the panels, quite a bit of pressure and heat, and they fuse to each other. So there is no lamination process. There is no adhesion process or adhesive chemicals that are used as opposed to lamination from the glass industry. And what you have is really a combination where you can pretty much put anything that you want together. Literally, we have artists that come to our office and they want to invent panels that have, amazing depths, where they use up to 12 different sheets of resin. This particular one uses 3. And you have a paper here which, by pressure, gives a texture to the panel itself. And you can make it very much scratch resistant or glossy, repairable, just by putting a paper on the outside. And you have a panel, you have a rice paper, another Eco Resin panel, a wire mesh, and another panel that a mold has been put on the side to create this texture now. So it's a very inventive process, really. And within that, the company itself has been very focused in innovation. The culture of the company is one in which you see people at the office and they're all extremely creative. It's a very busy environment. We've grown tremendously in the last few years, and there's a lot of, in some ways, stress, but it's exciting because it's the idea of being involved with very creative people. This is an example. We use a fabric that is just kind of an old look fabric. You have a very contemporary piece panel that you can create with that. The material platform today is one in which we're addressing many different materials. So we're evolving into a material solutions company. The architectural group at the office really focuses on finding solutions with all kinds of materials, and I'll show that in a minute on some of these projects. We have Eco Resin, which is a product that has a 40% recycled content within the product. You get lead points. It's translucent, it's versatile, durable. Polycarbonates, which is more of a structural product you can use for flooring. Chroma, which is made out of acrylic, and we have a process of embedding color within the material that makes it really fascinating looking, because chroma itself is very much or closer to glass than polyester-based resin panels or Eco Resin, by being that has the ability to distribute light in a beautiful way. We have a product that we just came up with, and we just developed this product, and a couple of months ago we received quite a few awards for it, and it's 100% recycled content within the product itself. So anything that has a label, any detergent bottles, any Coke bottles, anything that has a label of HDPE, you can actually send to our office, and we can make panels with it. And depending on the combination of the color, some bottles are orange, others are pink, or others are blue. You get different coloration within the panels. These are not translucent, they're actually opaque. And then we have a glass line, which follows somewhat of the same principle. It's made with a liquid lamination resin that takes a couple of days to catalyze. These three panels here have a fabric within the panels. The panels are 3/4 of an inch. You can literally embed many different things, not only fabrics, but botanicals and stones and almost anything within the glass pieces as you fabricate these panels. The panel itself, the benefits, is environmentally friendly, as I was just describing, with the 40% recycled content. It's half of the weight of glass, 40 times more resistant, ecologically friendly, it's color fast, post-consumer recyclable. So this is a panel, for example, that is made with 6 different layers, and you have a very interesting depth of the 3-dimensional look of the panel itself. We have also, we've taken a position in which, our manufacturing facility really focuses on being extremely environmentally conscious. Our CEO drives the company in a very interesting way to be sustainable. And for that, we have focused worldwide in addressing the needs, not only aesthetically of our panels to be inventive and to come up with new things, but also the needs of different communities around the world. We have a business model that we call Full Circle, and a series of panels that we have found. We have designers that go all around the world and try to find different places, Africa, Indonesia, et cetera, where there might be a need to generate some business, to generate some economies. What we've done in Africa, for example, with a panel called Ithemba, which means hope in Xhosa speaking African, that's this panel. It's a series of beads that come together with a wire, and they're actually put together by artisans, women that are in some way affected by HIV or AIDS. And what we do is we partner with a non-profit organization to generate a source of income for these people. We do the same with Capis to help those affected by the tsunami, by the recent tsunami, and we address sustainability of harvesting these shells, and we put them in panels, as you can see here. This is Palau, a process whereby husks that naturally fall to the ground are collected, and then we generate some business, we buy them and create panels, as well as lasso and river rock. So it's a really interesting business model, within the company. And apart from being very environmentally conscious, we want to address innovation in architecture. So that's why I joined the company a couple of years ago. I came from, as Marissa mentioned, architecture school. I went to UC Berkeley and practiced for a few years, and then got involved in an MBA program in a company called CTEK. CTEK actually we fabricated the, it was a company that had three divisions: aerospace, architecture, and automotive. We fabricated the cars for the Minority Report film. We fabricated the glass for the Condé Nast cafeteria for Frangaria. I don't know if you've seen the project, but it was the first time in architecture the glass was actually shaped with those shapes, amazingly complicated geometries and compound geometries. And it was a process of technology transfer where we took lamination techniques of automotive windshields. We changed it, changed the mold making process, changed the ovens, changed the way in which you use lump glass to create this very, very complex shapes in glass. So I was involved with that company, and I became very interested in innovation. And during my MBA program, I researched quite a bit people like Neil. His last name actually is quite interesting. It's Gershenfeld, and I don't know if you are familiar with him, but he's the MIT director of Bits and Atoms, and we were in a conference together, and we talked a lot, and he's just fascinating. He's doing a research in networks where he's bringing the idea of having CNC technology as an everyday life occurrence, and he talks about the day in which you're not going to purchase products anymore. You will be purchasing a file. And you will generate and you will do anything to it, and you will actually have your own CNC machine or access to it very easily, that you can create your own things. And he literally is doing that today. He's buying files from different people, and with his technology at his MIT lab, he's making bicycles with polycarbonate panels, and it's really fascinating. Other people like Clayton Christensen have spoken about a technology called disruptive technology and innovation, mainly in the business circle. There's a lot of this in the business world, of product development, and how you take a product and develop it and have it be sustainable and last for many years, et cetera, et cetera. Clayton Christensen wrote a book called The Innovator's Dilemma that I highly recommend. A really fascinating book that talks about these disruptive technologies. Other people like Putnam and David Osfeld have written about networks, and that I'm going to speak about for a few minutes here, because I think it's a very interesting part of our business and how we connect with architects. It really addresses the idea of social capital, the idea of taking an element of society and making it an asset for a corporation. I'll talk about that more in a minute. If you look at what social capital is, it's really just the features of a social organization, such as trust and procedures, right? And that can improve the efficiency of a working society by facilitating action. So it really is not a complicated idea. It's trust and procedures that you take and you have an organization, a group of people that can work in an efficient way. We all know that innovation takes place at the conjuncture or at the intersection of different disciplines. I mean, that we've heard about this probably for 20 years or 30 years. But the idea of having these different disciplines really work together, where there is trust and there is procedures and there's a mental, emotional involvement on the same projects, is very difficult. To really literally put the automotive industry and architecture, put the automotive industry and aerospace industry together, involved within the same project, is a very difficult thing to do. Why? Because you don't have them within the same organization. And what that does, it creates a very difficult position for innovation, hence the idea of innovation being so difficult, really. Within social capital, you have two social networks, one of them which is sparse, open, as is described here. This is 3Form, this is our manufacturing facility, with dense networks, or different departments, which really are part of a dense network. It's really easy to get people emotionally involved in a project within an organization. It's much more difficult when you're working with automotive, with a G polymer, with glass, with aerospace, et cetera, et cetera. They're really open. Communication is not as efficient. And these two networks are different in themselves. They present an important opportunity. The sparse networks present an important opportunity to import knowledge, as I was describing, and offer power issues and autonomy. The dense social networks develop trust the exchange of tacit knowledge, the idea of taking the tacit knowledge and make it a explicit knowledge and organizational support. What we're doing at 3Form today is we're really bridging that gap, because the architectural group is becoming an element that begins to become part of the offices of different architects around the world, as well as part of the office. So we're able to in many ways, be more innovative. One of the main elements that allows us to do that is the type of services that we have at the office. I mean, you see people or companies like Zahner, I think that everybody knows about Zahner, and Permastelisa, CTEK, very strong fabricators. They actually do not manufacture anything. They buy materials and they shape them. They create different things with these materials. One of the main differences, and it's a subtle difference, but it's incredibly powerful at 3Form, is the fact that we're also manufacturers. We have an amazing amount of information when it comes to the product that we create. Apart from being manufacturers, we're architects. So we have an architectural group that can design and can engineer. We have structural engineers, mechanical engineers. We also have a product development department. We have a fabrication department, just like Zahner, just like CTEK with CNC technologies. So we focus very strong in digital fabrication. And all that put together allows us to really have a component which can address almost any project that we're asked to work on. What happens here is mainly that there's a structure of mutual participation, coordination, and action that is created behind the projects that we work on. And as I was mentioning, we really exist in as 3Form within architects' offices. And I'll describe that with the projects that I'm going to show right now. Let me go to the projects. These projects are interesting because they're in a position in which the architects have designed the projects, and in many ways, they've tried to come up with a solution that is not available today. Let me just put it that way. This project by Marcelo Spina, it was actually published in Architectural Record this month. He designed this building in Los Angeles, and he wanted to use a metal finish on the facade, but a translucent metal. So here we go. You know, one of those questions that come to us often, where can you do something with your panels that is not in the market today, that we can really literally invent something that is interesting. So we started looking at this, and as you see here, what we decided to do is develop a panel that could address the aesthetic intent. This facade is entirely out of resin, and you can see the complex geometry as it moves in and out and the different layers of the facade. Part of it is glass. This element here is glass, and this is all resin. I think that this is the first building, at least in the U.S., where you have a facade made out of resin that is actually curved and it has complex geometries. The way that these projects start is we have a series of requirements. The panels need to be for exterior application. Typically, we understand resin as not being capable of sustaining 20, 30 years of span because of exposure to weather. Wind loading, seismic structural requirements. This is in California. For this particular project, we're designing all the structural components, all the channel systems that hold the panels, all the curtain wall systems, the attachments to the main building structure. You have heat forming, twisting of panels, translucent metal, continuous ribbon surface with complicated connections between adjacent materials. That's glass to resin, and no exposed mechanical connections. That's actually a question that is a particular question of all these projects architects want today. Panels that have no exposed connections, so you can't really tell how they're connected to each other or how they're supported. We started with the panels. How do you develop a panel that is a metal finished panel and a translucent panel also? So we developed a process in which you can embed a pigment within the material as you're manufacturing the material. This is a different process of what I was describing originally, where you have sheets that you're pressing together, or panels that you're pressing together and capturing materials, wire meshes, or fabrics. This is, at the time that you're fabricating the sheet, you're embedding a pigment that is going to allow you to have certain coloration. It's a very economic panel, and this actually is driven by the budgets of this project. So we look at budgets in a very, very careful way. We actually are in a position in which, when we look at these projects, we make the projects real. Projects are extremely complicated, and we go through a process of series of steps to make sure that the project can actually be built. At the end, we finished with, if you look at here, you have 0.5 concentration, 0.05, 0.1, 0.25. So we changed the concentration of the pigment, and at the end, we ended with 0.5. You can see here, this is what the facade is going to look like. It's a panel that, non-lit, is very metallic looking. You're going to look at this facade, and it's going to look like metal. As you put light through it, this is the same pigmentation. You can see how transparent it becomes. So you're going to have, during the day, this look. And at night, when the lights go on, you'll see through the building, see people walking around the building, and you'll see the structure and the supporting trusses, which we're very carefully designing today. We have certain parameters that we work with, again, to make sure that this material is material that you can use for exterior applications. You can see here, we do tests to look at the changes in the material in a period of 10 years. 12,000 kilojoules of energy will, in 10 years, will change the material in such a way that your eye will not be able to notice. So the material itself, the lifespan is 30, 40 years. You have the structural properties of the material here that remain very much the same during the same amount of time. And then we work with the actual properties, the modulus of elasticity, the flexural modulus, to make sure that the panels compress and expand at a rate that we can actually work with. So we do a whole analysis, and that drives actually the structure, the design of the structure, because that's where you need to address the complexity of the expansion and the contraction, sometimes between different materials. This is a geometry rationalization. We begin to look at the shapes and see how it is that we could form these shapes and see the level of twists, et cetera, et cetera. And what in this particular case, I'm going to talk about this panel. It was originally designed, the building, and the files were sent to us. We began to look at the actual the parameters for the fabrication. You can look at this, and there's a bend here, a very significant bend on the material, and that's that element there. You can't really form that and achieve the quality of the panel that you want. So what we needed to do is begin to look at the parameters for the forming. First, the panels had to be 4 feet by 10 feet, because that's what we work with. The bends need to have fillets that are 2 inches, et cetera, et cetera. So we go through a process of defining, in some ways you can call it the design at the end. It brings a very interesting question about the actual design of projects today by architects that want to be extremely creative, where at the end of the day what we end up with is something different from what it was originally designed, and it really addresses the idea of bringing architects and manufacturers together to really come up with a final design of the projects. This is the change of this actual panel as you introduce these 2-inch fillets through the surface to make the smooth transition and not this very sharp line as it was originally designed. These are models. We fabricate everything from models. We do everything digitally. You can begin to see the structure here as lines, some of the panels. This is the actual structure of the building that we're connecting to. This is the facade, which now, by this time, it has changed. Originally, the glass came up to here, and these panels were going to be bending into the building. Now we've put a connection here from the panel to the glass. It actually makes this kind of void within the building facade, but it's a change that we've introduced in the design of the project. The structural design of the project is very important. All the structural elements are designed with certain rhythm. Why? Because they're going to be very apparent. You will see them through the panels as you turn on the lights in the building because of the translucency. So they have to have certain rhythm to them. This is an element of the process that we work with as we fabricate and put together these projects. There's a prototype. And we begin to look at what piece we're going to prototype, and we begin to design the structure. These are horizontal trusses that are holding the panels, holding the channels that hold the panels in place. So some of the sketches of the design of these trusses. You can see here the prototype is composed of 3 panels and the structure. This is the prototype review, the first prototype review. For this particular project, we had two phases of prototyping. You can look at the panels now, begin to analyze the trusses, begin to look at the panel connection, the finishes of the panels. One of the main elements of a prototyping is that we include everyone in the project. We want the contractors, we want the installers, we want the clients, the architect. Because these are not simple projects. You cannot take this project, create your construction documents, send them to a contractor and say, can you build it? The contractor will run so fast that will come up with a price that is 4 times the amount. This is really typically what happens with architecture. And I tell you, as I was practicing, the more creative that you are, the more difficult it is. I mean, it's really somewhat of a battle. It's interesting how it changes from when you're in school going through all this innovation and creativity, and then the real world is a challenge in that sense. See some of the structural elements here as they come together. This is a very interesting slide that shows the way in which we work. We literally work virtually. So we have a web conference application or software where we can show our screen, and within seconds we can allow people anywhere in the world to connect and look at our screen. So what happens is we have a project, and the architect's in Los Angeles, the contractor might be in Pennsylvania or New York, and we are all at the same time looking at the same screen, and we're designing, changing the details, looking at what can happen with these changes, et cetera, and everybody's making decisions in real time. Makes it very efficient. If you see here, these are the images, these are the photos of the prototype, and you can begin to look at some of the decisions that we're making on the details, some of the sketches. All of this is recorded and reanalyzed and looked at, and so in many ways, the idea of designing is also a question here, or challenge, by having design in real time. This is the second phase of the prototype. You here now see that we've introduced a soffit, a point support system. The channel here is much smaller, a smaller profile, because that's an aesthetic element that we consider important as we're building the first prototype. You can see that we've introduced a Z element here, a structural support, that addresses the horizontal location of these trusses in space. One of the main things that you have to look at on these projects is how do you put these things together? One thing is to be able to digitally fabricate things or digitally model things and have all these computers do all the work. But at the end of the day, what are you working with? Where are the building components? What structures of the buildings are you working with? And how are you going to locate these in space? So we begin to define a way in which we can do that. You see other elements here. Drawings that begin to address fabrication issues. And this is the last image that I have of this project. I have one more, I think, of the last prototype that took place about a week ago. But here, this is an important image because originally we had about 38 molds, 30 to 40 molds to be able to fabricate this project. It's a huge number of molds. The most is the most expensive item of the digital fabrication process. If you know about digital fabrication, you probably know about this. And we were able to actually minimize the number of molds to about 13 because we lump panels together and we can form them with one mold. This is a geometry rationalization that we go through where we change, again, in the design, but in a very subtle way. You really can't tell from the beginning of the design to this rationalization what the difference is. And instead of 39 molds or 38 molds, we have 13 molds, bringing the project to about half the cost, which is actually quite significant. These are some of the details. They're very rough images. I just got this, I think, yesterday, of the second phase of the prototype. And look at the structure being much better defined here. Some of the waterproofing, some of the panels here coming together, the soffit, the way that they're connected. The soffit is transparent, and the light comes through in this interstices between the panels, and it just shines on the panels, and it looks really beautiful. This is the next project. This is for Fidelity Finance. It's like a company like Morgan Stanley, a finance corporation, very large company. And it's designed by Perkins and Will. And they came to our office with this paper model, and they asked us, you know, we have this oval element. There's a series of 3 walls. How do we build this with your panels? This exterior wall curves in one direction, although it tilts back and forth, so the geometry becomes complex. This is the center wall, which is at a jib board, just for acoustic purposes, so sound doesn't travel back and forth. And the interior wall is a series of panels that are compound shapes. What that means is they curve vertically and they curve horizontally. To make it even a bit more complex, we have a series of monitors here, about 40% of the wall, and a counter space. This room, which is about 80 feet on the long section, is utilized by the executives of Fidelity to analyze the latest technologies in financial analysis. So they all get together and do presentations within these monitors that actually you can pull out and move. So it's an extremely complex series of geometries to fabricate this. We have the panels needed to be backlit. That's an important element. They digitally printed. They wanted this binary code printed on the panels. I'll show you in a minute. Compound curved panels, no exposed hardware again. And it's not like they gave us the hardware for this. We actually had to come up with the design of the hardware from the very first nut and bolt to everything. It's all custom design. We have all wood casework is covered with form panels, which is this element here. We have operable panels for wire management. So the panels on top of the counter are operable. They actually move up, so you can plug in computers and different elements. ADA limitations due to leaning panels, protrusions, et cetera, with this exterior wall. You have media-heavy project, multiple monitors, removable panels. We modeled the entire project, and we coordinated with the architect and the contractor to get this built. You can see the panels here. These are for the exterior elements of the exterior walls. They go from a light blue to a dark blue as you move around this space. They actually are very interesting looking. It creates a very interesting perspective as you move around it. But apart from the color, you have a series of binary code elements of financial analysis that you're matching from panel to panel. The fabrication of this is you print on a fabric the digital image, and then you embed the fabric in the panels. But the pressure and heat move the fabric. So how do you control that? We had to literally invent a process of templating to control the position of this fabric within the panels, to have the accuracy to be able to match the zero with the zero element here. As you can see here, these two, this is the final installation. You can see the zero here matching perfectly well within a curve that is actually leaning back and forth. It's really a complex set of issues that we, in many ways, learned a lot from this project at our company. This is a model itself. You can see there's monitors on the outside. There's all the monitors on the inside here. There's another series of monitors here. Every single structural component here is modeled. Every bolt, every nut, every piece, and everything is digitally fabricated, either with CNC or water jetting or laser jet cutting different elements to put this whole thing together. You can see a close-up here of the structure. It's a vertical extrusion system. This element here in the wire frame is a steel that controls the curvature of the panels in place. And you can see here there's a spring and a torsion spring mechanism. So what we're doing here is we're tapping on the back of the panels, only half the depth of the panel, so you don't see through the hardware, with a torsion spring mechanism that connects to this element. So when you put the panels in place, the torsion spring opens and it just sucks the panels in. If you want to remove them, you just pull them out, press the torsion spring, and basically take them off. And this entire hardware system was developed at our office. You can see the models here and some of the iterations as we went through the fabrication process. The assembly is also very important, and nesting. You know, some of these projects begin to really address a very interesting issue of sustainability. Today I was reading that a house, just a 2,000 square foot home that you build, generates about 8,000 pounds of waste. I mean, it's a huge number. When you look at a project like this, completely fabricated with CNC technology and digital technology, what you have is minimum waste because you are nesting. You know, you're actually literally flattening the areas here and cutting the steel, water jet cutting the steel, getting it to the facility to assemble, and you have very little waste. So you're not recycling a lot of material. This is a very powerful image of every single piece of hardware. We assemble every single one of these at our offices. You can see there are different curvatures on some of them, different lengths, different elements. We sent to the site a series of templates for them to locate on the floor, and then every single template had a location of these elements, so they could begin to really literally assemble this like a puzzle. Put every single piece of hardware in place, and then come in and put the panels in place and build this entire project. This allows you to understand a little bit of the depth in which we get involved in the project. Look at the number of sections here. Hundreds of sections that we had to cut to get information, detailed information of every single piece of hardware that was fabricated for this project. Here you have the templates. This is the prototype phase. This is the template that locates the structure. This is the center wall, and this is the exterior wall. This is a fabrication area as they were making the panels. This is the wall being erected with all the structure in place here. This is the interior panel prototype. The exterior is on the other side. The exterior looks like this. You now can see that the structure doesn't go through, but it leaves this somewhat subtle shadows in the prototype of the structure. The panels were not, the digital prints were not defined at this phase. That's why they're green and they're not blue, and they don't have the digital image within them. This is a review of the prototype. You can begin to see really what this whole thing is going to look like. The monitors, the counter, lighting, and obviously everybody, again, is involved in the prototype phase. Some of the images of what this is to look like at the end. You see the monitors here, monitors in here, every single piece of hardware. Again, you could only create these by modeling this entire thing. It's an interesting process because we use Rhino, and then we also use ArchiCAD. And there's a very interesting way of changing the Rhino files and exporting them to ArchiCAD, and ArchiCAD being parametric changes the entire project. So it's a difficult project to work entirely in Rhino with, because you can't have records of the changes. This is the installation here. You can begin to see the panels in the interior, some of the hardware. The hardware actually looks beautiful as you see through in between the panels with every single component, the light. We wanted to at some point leave this open, but we actually enclosed it. Some of the other hardware elements, the torsion spring mechanisms that you can see here, and the very complex shapes of the interior walls. You see the areas of the monitors. This is what it looks like as it was being installed. These are the final images. This is a 10-foot door, a slider, curved, which we literally fabricated an entire new hardware system, so it can actually be a hanging element that is a pocket door that goes in between these walls here. This is what it looks like today, finished. This is lit. That's non-lit. This is the interior. It's really a very interesting structure, and that it begins to address many issues of how it is that you work together with architects to be able to achieve something like this. I'm going to go through this project somewhat quickly. This is a project in which we began to combine now, because of the material solutions, the ability to have different materials to use here. We began to combine glass and resin to literally invent a panel that can have very, very strong structural properties. This is for the entrance of the Cirque du Soleil in Las Vegas, the new one. This is an association between, I don't know, Paul McCartney, Steve Jobs, the Mirage, and the Cirque. The main entrance is a floor that turns into a wall, and it turns into a ceiling. It's about 10 feet wide and a 70-foot run from here to here. Panels, you can see the thickness of the panels. They had to be fritted, so there's a frit pattern for ADA compliance and slippage. We used different materials here for lighting purposes, aging tests, lighting tests, structural design. All these beams are made out of glass and resin combination that support the panels. You can see the channels. All the channels, all the structure was designed at our office and fabricated at our office. You can see the elements of indexing the panels with these elements, the channel systems. And the tolerances had to be very high to be able to put all these elements together. Failure tests on the panels, independent failure tests, more prototypes, measuring of the tolerances. You can see the accuracy of the geometry here. The prototype is actually 5 feet wide, although the project is 10 feet wide. Some other images of the prototype. We literally had to invent tooling that could allow us to control the gauges of the material to different tolerances to be able to have this fit perfectly well in place. These are the glass beams. And again, they're glass and resin. These are 10 feet long, 2x4s. So you can begin to think about a solid piece of glass that is 2x4, 10 feet long. It's extremely difficult to work with. The resin makes it lighter. It makes it stronger, much easier to work with it. We had to design structural support systems inside trucks to be able to ship all these items. It's coming together. The LED system, the lighting is unbelievable. We weren't involved in the design of the lighting systems, but there isn't 1 inch here that doesn't have an LED panel. It's RGB LED computer control. So it begins to change in an amazingly dramatic way. It just changes the whole space. You can see here. And there's the Beatles right there. This is the last project, and is Dylan and Scofidio. And they came to our office, a year and a half ago, a couple of years ago, when they won the award for the Lincoln Center project. And this is a section of the Ali Stolly Hall. The Lincoln Center proper is a series of 3 or 4 different buildings that they're going to be changing in a significant way. There's a lot of publicity on the Lincoln Center project itself because they're the last brutalist buildings in New York, and a lot of people don't want to change them. But in particular, the Ali Stolly Hall, a section through it, the design called for this white surface to be a solid wood material. with real wood, obviously. You see today concert halls are like that. We have very, very rich wood inside. But the orange area is translucent wood, and it's real wood. So real wood translucent panel. And obviously when they came to our office, it was like, you know, everybody's scratching their heads. Well, they don't exist. And this is an interesting position. I was, Marissa and I were talking about this last night, where the award was actually given to Dylan Scofidio for this project, but the panels didn't exist. So it's a very interesting position to take, where as an architect you're driving innovation in that level and achieving a level of confidence from all the parties involved, all the executives and the president of the Lincoln Center, to say, yeah, sure, you know, let's go ahead and move with this. These are models of the interior of the, this is the balcony, these are some of the walls, these are some of the models that we started working with. Here we have translucent wood panels. They had to be 1 inch thick. Class A material for fire rating. This is a public building, it had to be Class A. MEA approval, this is a toxicity entity that exists only in New York. It's really kind of odd, because they put the panels to the test where they kill rats. It's funny, but in all the places but New York, and you have to do that. Formable to various complex geometries. No differentiation between solid and translucent wood panels. So when you see the solid wood panels and the translucent wood, and they're non-lit, they're literally identical. Capable of sequencing the wood throughout the entire hall, and capable of addressing acoustic requirements. This is the wood. We began to look at what wood we could actually use. There's only 2 companies in the world, they're both in Japan, that can manufacture, they can cut a tree with slices of 0.2 millimeters thick. That cannot, there's no other companies that can do this. And as a matter of fact, I was just in Tokyo with Liz and other people selecting the actual flitches for the particular walls for the project, and the company would not show us the cutting process. They wouldn't take us to the actual place. This is some high secret. In any case, they cut the material and they put a polyester backing on it that makes the wood just a little bit supple, enough for us to be able to actually work with. And this is the way that we actually receive the panels at the office. For material development, we started to work with a very interesting technology. This is, if you put the panels through the same process that we have for manufacturing, which is pressure and heat, you will break the wood. It's very, very thin. So we began to look at other industries and analyze different technologies, and we came up with a brand new process to be able to put the material right at the top surface. So what you have is a 1/32 of an inch resin panel on top. Right below that you have the 0.2 millimeter thick wood, and then under that you have a 1 inch thick panel. So you don't see the 1/32 of an inch resin panel that covers and protects the wood. And this is a somewhat of a juxtaposition of a lamination process and a pressurized process. From that point, after we fabricated this panel, which is something that we do at our company, we get involved in investing our resources to come up with the first solutions that we're asked for by the architects. We were then contracted to do these shapes. In resin itself, in 1 inch thick material, is very hard to do in these shapes. And now you put wood, and it makes it much more complicated. So we began to do a lot of different tests, and we came up with a solution for it. So we were able to fabricate the panel within that shape, and you can see it being translucent. It's a very, very rich looking wood. There's the other images of the process. This is, we can't fabricate a solid 1 inch resin panel. So these are 2 half-inch panels that are put together, and then the wood on top. From the panel, then we moved to a process, and we moved to the fabrication of an entire wall, a piece that represented the interior of the alley SOLEIL hall. Now you have a 30-foot wall, 30 feet high, 12-inch wide, which it's composed of 24 panels. And this particular wall was used to approve the entire project. I mean, this is one of those cases in which you needed to get this done and have a meeting with the Lincoln Center officials, Turner Construction, everybody else involved in the project, and say, let's go ahead and move with the project. Because before that, again, there was no translucent wood panels, and there was no publicity behind this. Nobody talked about them either. But when you begin to look at this entire wall, then you have to deal with the sequencing of the wood. When you look at real wood, you now have flitches that you select, book matching or slip matching fabrication processes, and I'm not sure if you know about this, but the way they cut the wood and they slice it together and they glue it together, it's very critical because of the veneers. And in this particular case, when you use real wood, you have sequencing. That means that you use the panels, and you look at the grain, and when you look at a wall, you see the grain throughout the walls continue all the way around the concert hall. You can only do that with real wood. So there's some very tricky and important issues that you have to deal with. You can see the wood here. You pull it the wrong direction, very easily just splits. But again, you can achieve very complex curves if you do it the right way. We fabricated all this digitally. As you can see, this is our fabrication department. We have a 5-ax machine that created the molds off of this digital file. And you see the mold making process here, the tool for the machine going around and creating the precise molds for us to be able to form the panels. You can see here the panel itself being cut by the router. So what we do is we create the mold, we heat form the piece on top of the mold, we then take the mold and the piece and put it back in the CNC machine, re-index it, and then trim it to extremely accurate precision. So then you can take this, finish it, and then put it on the wall together as a puzzle. It's almost that simple as I was describing. Yeah, almost. This is rationalization of the geometry where there's places where the wood would not take the shape. When you have a curvature here, which is actually a ruled surface, you know, it's not a complex geometry, but it flattens at this point. When it flattens, the wood won't take that shape. So we actually had to get into web conferences, and you know, Duns Coffee in New York, Turner in New York, and us in our facilities looked at this panel. We actually decided at the end to cut the panel in half, and you'll see it on the final piece. This is a model of the structure. We designed the point support so we could have and address tolerances in the way in which you actually place the panels. Again, another project where you can't have hardware exposed. You can see the little shadows here, and that's because we're actually tapping on the back of the panels also to support these panels in place. Design a structure that allows flexibility in and out, about 1/4 of an inch to control the position of the panels in the wall. These elements are actually placed on the panels before the panels are hung. You see here the panels as they're being finished, these elements attached to them. In some ways, if I can describe to you, and it would take quite a bit of time, but the idea of being able to locate these points within a curve is extremely hard, and keep the tolerances of the geometries and locate them in a way in which at the end of the day you're going to have a perfect wall system. That is not a simple process. Panel-to-panel connections we define as spline. We created a spline that could be done with the same material. You see the accuracy of the geometry here. This is the finishes. We do this slightly. We sand the surface and then we finish it, and it just looks just really beautiful, gorgeous. This is dry fitting. With the CNC technology, we cut the tools down here that support these elements in place and address the curvature of the elements, and then we can begin to dry fit. And by dry fitting, we can position the location of these holes within the panels and make sure that everything is precise. You can see here as it's actually coming together, other images. Again, it's like a puzzle as they're being put in place. We put paper elements on the panels to protect them. There's a list there, and this is the wall itself, images of the wall. You can see this is the panel that I was mentioning to you, that it's cut in half. And look at the grain and the transition of the grain from panel to panel in the sequencing. These are translucent panels. This is solid, and this is translucent. So there's really no difference. This is a place in which you're actually going to walk in. You're going to see this very, very rich environment of beautiful wood, and it's going to be non-lit. And then the performance is going to start, the lights are going to dim, and then suddenly the walls are going to glow with wood. So it's in some ways one of those areas where you begin to really look at a material that has never done that before, and it just creates a whole different character within the space. Here you have a transition from the floor to the wall, and there's a transition from the wall to the ceiling and all the way around. This is an element where you're fabricating hundreds of panels, fabricating the structure, and you're coming to the side within a cocoon that is made out of a concrete shell, and you're putting this whole thing in place, and everything has to fit perfectly well, and everything digitally fabricated. So you have to know exactly what to do. It's essential that you have experience of working on these projects. We're actually working with CATIA for this particular project. We're now introducing CATIA to the company, because it really allows to control parametrically much better all the tolerances. You can see the wall here. I'm going to show you like 8 images. I show you the changes on the wall with the light. This is a rendering of the concert hall. The wall that we built is this particular piece here. You have the cone shape of the balcony. The balcony is going to be translucent. All this is going to be translucent. The front stage, several panels are going to be translucent, certainly on both sides. And it's interesting. This could not be built in accordance to the architect's vision, certainly, without the invention of these translucent wood panels. And then symbiotically, we really developed a new product process. We invented a new technology. Now we're taking that technology and it's allowing us to make all kinds of panels. So in an interesting way, we take the idea of being innovative, and it serves a great purpose for the company itself as a manufacturer. We've developed patents. We have patents on the structure for the FIDELITY project, for many different elements. I think it's very close to 6 o'clock now. This is all that I have today. Hopefully you found this somewhat interesting. It really is the idea of changing the way the manufacturers work with architects. Somewhat unusual that you can, as an architect, pick up the phone and call a manufacturing facility and say, look, I want to do all these crazy things. Can I have your facility to work with me on this? I can probably take a few minutes right now and answer some questions if you have questions. No questions? Well, thank you very much. Thanks for your time.